So here we're asked to consider the model of a vehicle moving through the air, which is provided to us in this differential equation. So V is the velocity of the vehicle, F is the force, K is a drag parameter. And we're also given the mass of the vehicle, which is 1,000 kilograms, and this K parameter. So what we're asked to do firstly is linearize the model about steady state, and we're given our steady state is F bar equals 1,000. And then once we've got that, we want to turn it into a transfer function with the V dash and F dash. Remember, the dash is deviations from steady state for our system. So let's start with A, and that is to find our equilibrium position. So at equilibrium, what we know is that all of the time derivatives are going to be equal to 0. Okay, they're not changing over time. So that means that this V dash here, or V dot I should say, V dot here, its equilibrium, which I'm designating with the bar, is going to be equal to 0. Okay, M is just a constant, and we know it's this 1,000 here. F, that's our force, and potentially that can change over time, but we're told that we're looking at it at steady state of 1,000. So let's note that in. K is again a constant, but we were given its value, and V is velocity, which could change over time, and we're going to need to know its steady state, and we weren't given it, so I'm going to leave that as a question mark for the moment. So we should be able to go and find it though by substituting all this known stuff into our equation. So V dot I should say. It's confusing with the dashes and the dots. Alright, so that's our equation. So at equilibrium, we've said that this V dot is equal to 0. So that goes away. We've got F at equilibrium, which is equal to 1,000, minus K is a constant, so it's always going to be this 10, and V at equilibrium is what we are going to need to find. So let's sub it in as V bar. So rearranging this equation, I might shift this to the other side, and we get 10 V bar squared equals 1,000. If we divide by 10, we're going to end up with 100. So V bar is going to be the square root of 100, which is the same as 10, and it's a velocity, so it's going to be in meters per second. So that's our equilibrium value for this variable. So let me pop it here. So now that we've done that, we want to try and do the linearization part where we apply Taylor series. So let's call that step 2. So apply, I'll put TS for Taylor series, and it's about our equilibrium position that we've just identified. Alright, so going back up to our question, so the only part that really needs to be linearized is this kv squared part, okay? It's the v squared that's not linear. So what I'm actually going to do though is I'm going to linearize the whole thing at once, just so that then we end up with everything in one nice, one long equation that we can manipulate. Okay. As an alternative, if you wanted to, you could just look at this part on its own. So if I'm going to do the whole thing at once, it's going to be worth putting everything onto one side of the equation. So I'm going to move this mv dot onto the right. So that means that our equation becomes 0 equals f minus kv squared minus that mv dot. So I'm going to write this as being a function though. So the function is of the things that could potentially change with time, and we just identified those a moment ago. It was the force, the velocity, and the derivative of velocity, so acceleration. So let's pop those into our function. So f, v, and v dot. And I'm just going to set it to all of this. Cool. Alright, so now we can apply our Taylor series, and remember that that means we need to take the derivative of our function f with respect to each of these different variables, and then evaluate at what that derivative is at our point of interest, so at equilibrium. So I'm going to do this as a pre-step before we sub in. So let's start with taking the derivative with respect to capital F, our force. Alright, so the derivative here is just going to be 1, and then neither of these have f in them, so the derivative would be 0. So if we were to then evaluate this at our equilibrium position, it's going to be really easy because 1 is just 1. Alright, so that one's done. So let's move on to the next variable, which is v. And looking over here, taking the derivative with respect to v. All right, this term and this term don't have a v, so their derivatives would be 0. But we can take the derivative of this middle one. So it's like going to be the top number times the front number, which is -2. The constant is k out the front, and then take 1 off the power, which is just going to be v to the power of 1. So that's our derivative, and then evaluating it at equilibrium. So 2 times k, all right, we were given that constant back up the top here, it was equal to 10. And then the other thing we needed was our velocity at our equilibrium position, and we solved for that a moment ago. We decided that it was the 10 meters per second. So popping that in. So that works out to, I think, -200 for the derivative at that point. All right, so we have one left to go, which is taking the derivative with respect to our third variable, which is v dot. So looking at this, again, these first two terms don't have a v dot, so their derivative is 0. Derivative here, though, is going to go to -m. So if we evaluate that at our equilibrium, it's just going to end up being -m, and m was equal to 1,000 kilograms. Cool. All right, so now let's write out the Taylor series expansion of our function here. So the function is approximately equal to its value at equilibrium, so that's with the bars over the top, plus the derivative with respect to each of our variables evaluated at equilibrium, and then multiplied by the difference between the variable and the steady state value. So just writing that out for the last two, so v and then v dot. Oh, sorry, I missed the equilibrium. Cool. All right, so substituting in here. Now what we should find is that when we evaluate the function at equilibrium, it should go to 0. Okay, if it doesn't, you have made a mistake, and you can always check it just by substituting into this function with all the equilibrium values. All right, so next we have our derivative with respect to f, which we found to be equal to 1, multiplied by f minus f bar, plus the derivative with respect to v, which we evaluated to be -200. So let me go back and write this as -200, multiplied by v minus v bar. And then this last one here is -1000, multiplied by v dot minus v dot bar. Now, if you wanted to, you could substitute in the values here, but I'm just going to leave it and swap them over into the dashes version, which is where we take it as the deviation from equilibrium. Before we get to that though, I forgot almost that this side here, that side is directly just equal to 0 in our case from this part. So I can pop in 0 on the left. Alright, so let's go over and change these into our deviation variables. So we can just basically directly write it in. So f dash is equal to the difference between the variable and its equilibrium. Here we've got, it's going to be v dash, which is the difference between the variable and its equilibrium. And here it's going to be v dot dash. Alright, so that there is our linearized equation. Okay, you can see that we have just constants out the front of all our variables, and they're all just variables on their own, alright? They're not inside a sign or squared or anything like that. So that's what we were looking for to answer, I think, part A of this question. So part B is now to change this into a transfer function where we want v dash on f dash in the frequency domain. So jumping down, what we're going to want to do first of all is take the Laplace transform of this function. So 0 is going to be equal to, this is going to stay as f dash, this is going to stay as v dash, but this one has a derivative on it. So when we Laplace it, it's going to get an s. Alright, so next what I might do is swing these two terms to the other side of the equation. So 200 plus 1000 s v dash is equal to f dash. And then we might factorize. So we're going to get 200 plus 1000s is equal to f dash. This as v dash divided by f dash. So if I divide this down and divide the other down, we're going to get 200 plus 1000s. And of course we could make this a little bit nicer by getting a 1 in front of the s. So if we divide top and bottom lines by 1000, we're going to end up with that. So it's 1 on 1000 over, this is going to become s plus 0.2. And again, if we want to, we can write it with the little functions of s. Cool. So that there becomes our transfer function. So that's pretty much all there is then for this video, and I'll see you in another one.